Hello, my name is Cameron Connor, and today I will present my report on structural credit risk models. My project explores how we can use stochastic calculus and numerical methods to model the probability that a firm will default on its debt. We look at two models specifically, the Merton model and the Black-Cox model. The motivation behind this project is my upcoming internship at the Bank of America in the investment banking credit team working on models like this. Let's start with the Merton model, which is foundational because an extension of this model was bought out by Moody and used in their models to this day. The model is built on the idea that a company is financed by equity and debt. It is structured because the model uses the current share price to calculate a probability of default. Equity gives you voting rights and has unlimited potential return, whereas debt gives a fixed return and greater security, because in the event of liquidation, debt will be paid back before debt equity is paid out. For the Merton model, we assume that equity has no dividends and that debt is a zero coupon bond. This gives rise to a few formulas. We can say that the value is equal to the equity plus the debt, all measured at the present moment. We can say that the future debt is the smaller of the debt multiplied by the interest or the value of the company. And we can say that the future equity is the maximum of 0 and the difference between the firm's future value and its debt. Let's illuminate this with some examples. In the best case scenario, when the value of the company is higher than the debt, the company is doing well and is still in business. Therefore, as a priority, the debt is fully paid off, and the equity of the company, the remaining upside for shareholders, is paid out at VT minus D. In a worst case scenario, the company performs poorly, and VT, the value of the company, is less than the debt, D. The company becomes insolvent, and debtors, as a priority, recover the remaining value of the company, and the equity becomes valued at 0, and the shareholders receive nothing. Let's look at the payoff diagrams to get the big idea of the Merton model. Equity acts like a long call. The original investment in the equity, is like the premium for a long call option, whereas debt behaves like a short put on a company. This means that we can use the Black-Scholes model for equity and for debt. However, for this, we have to assume that we know the asset value and the volatility of the asset value at all times, which in practice is quite challenging. But as we've established the Merton model's usefulness, let's look at how it can be numerically simulated. At the top here, we can model the asset value as a stochastic differential equation following geometric Brownian motion. And then we're going to move on, and I investigated two discretization schemes, Euler-Maruyama and Milstein. The critical difference, which has been circled in the bottom right, is that the Milstein scheme includes a first-order correction term derived from the Ito-Taylor expansion. This term is mathematically necessary because our diffusion term is state-dependent, meaning that the noise will scale directly with the asset value. I conducted a simulation using 9 million paths to verify this scheme, and I used this because I wanted to use a high number of paths to minimize the Monte Carlo sampling error, ensuring that the residual noise would not obscure the underlying convergence rates. And as we can see here, the log-log plots confirm the theoretical expectations. While both schemes perform identically for weak convergence, the Milstein scheme achieves a strong convergence slope of 1, effectively doubling the 0.5 slope of the Euler-Maruyama method. This result is the empirical proof that Milstein provides the significantly higher accuracy required for more complex financial derivatives. This brings us to the Black-Cox model, which addresses the primary weakness of the Merton model, the fact that in the world of finance, defaulting can happen at any time, not just at time of maturity. By treating defaulting as a first passage time event, where insolvency can occur the moment the asset value hits a barrier, in this case L, from above, we can capture the reality of temporary liquidity crises. This path dependency is exactly why the strong convergence of the Milstein scheme is so vital. In a barrier model, if our simulated trajectories are noisy, we risk missing a barrier breach between time steps, leading to a systematic underestimation of the probability of default. We can correctly say that volatility affects creditworthiness throughout the period of a loan, which the Merton model does not account for. In conclusion, the project has determined that structural credit risk modelling is a balance between financial theory and the integrity of numerical analysis. While the Merton model remains an essential theoretical benchmark, its point in time limitation fails to capture the volatility within a day that happens in modern insolvency. By transitioning to the Black-Cox framework and utilising the superior strong convergence of the Milstein scheme, we create a model that respects the continuous nature of risk.